And our next presenter is John Sullivan-Fedock from University of Pennsylvania. He is a researcher of T.C. Chan Center for Building Simulation and Energy Studies in University of Pennsylvania. And his research interest is the building simulation for energy studies and for use better building design. So ladies and gentlemen, please welcome Mr. John Sullivan-Fedock.
All right, I'm John Sullivan from the T.C. Chan Center, and I'm going to be talking about increasing the effectiveness of wind energy harvesting with CFD simulation-driven evolutionary computation. Is anybody familiar with evolutionary computation? Nobody. All right. I'm going to start by talking about good designs and ask you, what if I could design for you a high-res optical telescope that self-assembles? There's our high-res. Or what if I could design a computer rivaling the complexity of, or rivaling the connectivity of every system on Earth that runs on the power of a light bulb? Or finally, a tall building built and operated for hundreds of years on nothing but solar power. The philosopher Dan Dennett points out that these are both fruits on the tree of life, although designed by very different processes. Evolutionary computation is the process of mimicking biological evolution, and people have been thinking about using computers this way since World War II. John Koza documents the results, which he defines as human competitive, in dozens of fields, meaning that he has used evolutionary computation to achieve results equal or better than what a human designer could produce in these and other fields. Evolutionary engineering is evolutionary computation applied to design. Coupling the evolutionary computation techniques with computational fluid dynamics is a technique that's been used in engine aircraft design. If any of you came over on a Boeing 777, then the engines on the wing of that plane were optimized in this way. As far as application to buildings, if you were over in any of the BIM talks, you already saw some of the application to structural engineering. I'll go into some of the application for daylighting and passive systems before touching on wind harvesting. This is a basic rundown of how a GA works. An initial population is produced and tested against some objective, which is tested for fitness, and then a new population is generated, retested, and runs through this loop, continually optimizing for whatever your goal is. In nature, the goal is reproduction. In our case, it's accumulating, it may be good daylighting energy or wind harvesting. This is an example. You can see the populations moving from 1 to over 200 generations this is the facade, which is being optimized for daylighting. This is a project by a colleague of mine, Mustafa Sadeghipour from UPenn, who's now at Smith & Gill. And every aspect of this was optimized by GA. There were about 40 parameters, and it was optimized for daylighting as well as for energy consumption. And you can notice how closely the evolution of the building matches evolution in nature. This is a study where fruit flies are selected for phototaxis, or sensitivity to light, and in a mere 20 generations show noticeable change. this mimics what we see in our building optimization process. So I'm getting a little feedback up here. Is that coming through? All right. So the diversity of wind power potential in the built environment is explored. We have the three basic building-augmented wind turbine configurations, either taking advantage of accelerated wind speed over the top of the building, using the buildings to channel wind between, as in the Bahrain World Trade Center, or punching holes through the buildings. This shows, on a typical wind turbine, the amount of power generated compared to the wind speed. So you have a cut-in speed and a cut-out speed. And to optimize, you want to float around here. Also, as your elevation increases, the potential of the wind that you could harvest increases. Other problems, the wind potential varies in different regions. Whether you have steady wind or whether you have erratic wind, whether it's omnidirectional or comes from a predictable direction. Also, surrounding buildings interfere and cause a lot of turbulence. So all of these factors can be addressed with an evolutionary approach. So that whatever the surrounding conditions, whatever the wind curve where you are, your building will adapt to that specific setting. These are some of the various studies developed, that we developed as part of a DOE grant for optimization. In this tower was designed to be omnidirectional in a fairly steady wind stream, so that as the wind changes directions, creating high and low pressure, turbines would track and the facade would channel the wind to the turbines. And then gardens were placed on the corners to deal with some of the noise issues that can arise from these. In order to optimize the facade, it had to be controlled, and a lot of the parametric processes that you may or may not be familiar with attempt to do this. This is a process developed by E&Q at the Chan Center for agent control of the geometry, whereby one agent point will control several other nodes that will control the facade of the building. And we found that using this technique to optimize or to control the facade for optimization, you can actually converge much quicker than you could using direct control in most of these studies. So over here we have a direct control where we're trying to, this is a light level study, we're trying to move in on 500 lux. And over a dozen generations, it approaches about 1,000. Here it converges almost immediately using the agent system. This is exactly the same study, just the difference is the control system. If anybody's interested in this agent system, you can talk to me afterwards and I can send you a journal. Most of the problems that we're dealing with are complex problems, excuse me, which is what evolutionary engineering is most useful for. Reducing problems like this or isolating variables doesn't work. If this is a simple problem from a thesis by Nathaniel Jones where there are only two variables being modified. There's roof slope and rotation. And you'll notice that if you try to optimize for one of these and then try to optimize for the other, you may miss some of the most optimal solutions. And so the only way without something like a GA to plot this space would be to run all of these simulations and map out this whole space. And that's just for 2 parameters. So when you start to get to many parameters necessary for a facade like this, you reach a world of potentials, these billions and billions and billions of potential buildings, and it just becomes impossible to simulate all of that, to test all possible contingencies. Now, some of these will be optimal solutions, but most will not, and some may be optimal solutions in particular environments. So our objective was to maximize the total power generated. And on our wind curve here, the facade was being modified as well as the size of the wind turbines, which followed from the size of the facade. This is if we had one parameter, the amount of power generated. If we had two parameters, and it goes up. So this is an example of the optimization process for power output. And you can see we start moving through. At the beginning, the system is trying as much variation as possible, and then it starts to hone in on the same solution. These start to converge, and now it's basically settled. So we can be confident that if this is not the optimal solution and configuration, it's at least very high. And to review the genetic process, after the solution is optimized, you can do a more thorough testing and compare the results to your base case either with CFD or with wind tunnel analysis. You couldn't do wind tunnel analysis through the optimization process because you would have to build hundreds of models, but once you have an optimal, you can use this for verification. So comparing, in this case, the base case, which was designed by rule of thumb and used simulations for verification, the potential changes must be isolated. The genetic algorithm used simulation continuously, and depending on the study, we found could produce up to 32% more power in the same environment, and all potential changes are optimized simultaneously. So depending on your environment and depending on your goals, there may be many peaks. Perhaps this building is optimized for a certain environment, and this building for another, and this building for another, depending what you're trying to do, and depending where you are. So the pros and cons of this method. It's pros useful for feasibility studies and verification, can provide multiple peak solutions, is adaptive to the environment, and will often find surprisingly innovative solutions, especially to complex combinatorial problems. Cons, it can be computationally expensive and slow compared to isolating variables, although fast compared to checking all possible contingencies. So thank you for your time, and thanks to CTBUH, Transolar, Professor Dan Dennett, Steve Kimbrough, and Ji-Hoon Kim for the help. And I guess we're leaving questions, so.